Next, consider the diagonalization of a matrix. So here the matrix is said to be diagonalized if we get the matrix in such a way that it will be consisting of the elements only in the diagonal. So here for example, if you want the matrix A to be diagonalized, and it is possible if the number of eigenvectors are same as the order of the square matrix. It means that whatever the matrix we want to diagonalize, so suppose if A is of the order 3 cross 3, then eigenvector should also be of the order 3 cross 3. So in such cases we can say that the given matrix can be diagonalized. So here in order to diagonalize the matrix, we need to perform the operation P inverse dot A dot P. That is, the inverse of the matrix P has to be obtained, and then that has to be scalar multiplied with the matrix A and the P. So here we can see here, let us assume, so P as a matrix of eigenvector, so which can be written as P is equal to x1, x2, x3. So here for example, we are going to assume x1 as 2, 1, 4, x2 as 1, 1, 2, x3 as 0, 1, 1. So here using this P, so here P inverse can be obtained using the equation adjacent P by determinant of P. So here this adjacent P, it can be obtained using the equation cofactor of P to the transpose. So here already we have seen how to obtain the cofactor of P. So here cofactor of P, it can be obtained as shown here. So here as you can see, so this is the given matrix. So here for each and every element we can get the cofactor value. So for example, for the first element, the cofactor can be represented as C11. So here which will be obtained as minus 1 to the power 1 plus 1. Now leave the first row and first column. So the minor will be 1 minus 2, which is equal to minus 1. Similarly, for the second element, the cofactor is C12, for which we can write minus 1 to the power 1 plus 2 into, now leave the first row and second column, so which will be 1 minus 4 as the minor. That is 3 will be obtained as the cofactor. So like this, so we are going to use you are going to make the calculation for each and every element to get the cofactor. So now here you can see that whatever the matrix here we have written, so here I have written P, so but it is a cofactor of P matrix. So here these are the cofactors that are obtained. So these cofactor of the matrix P, it has to be transposed so that it gives the equation of adjacent P. So here that can be done by making the first row element minus 1, 3, minus 2 into the column, and bring the second row element into the second column and the third row element into the third column. Next, we require the determinant of P value. So here calculate the determinant P using the cofactor expansion formula for the given assumed matrix P. So and that will be obtained as 1. So now using the values of the adjacent P and the determinant P, here we can obtain the equation of P inverse. So here P inverse is equal to, so here this represents the adjacent P and divided by 1 represents the determinant of P. So substituting, we will be getting the equation or the matrix of P inverse. So now as earlier I said, so the matrix A has to be diagonalized. So here we are going to assume the matrix A. So here you can in this example here you can see that, so here we have taken this 4 2 minus 2 minus 5 3 2 minus 2 4 1 as the matrix A. So this matrix A has to be diagonalized. So here in order to perform the diagonalization, so first we are going to multiply this A with P inverse, and then whatever the result that is obtained, that will be multiplied with the P. So here as we know, so here the multiplication can be done by multiplying the first row with the first column element to get the first element of the first row. Similarly, the first row will be multiplied with the second column element to get the second element of the first row, and like this you continue with all the multiplication to get the elements of P inverse A. P inverse A as shown here. Okay. So after the performance of P inverse dot A. So this is the matrix that has been resulted. So you multiply this P inverse A with P. So in the same way, you just multiply the first row with the first column to get the first element of the matrix, and so on. So here after the simplification, you can see that. So here we have obtained the diagonalized matrix as 1 0 0 0 2 0 0 0 5. So here you can see that the elements are present only in the diagonal of a matrix. So these diagonal elements, they can be represented as lambda 1, lambda 2, lambda 3. So here lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 5. So here we can say that the P inverse AP, it is a diagonal matrix, and it can be represented as capital D. And one more thing we need to remember, that suppose if two eigenvectors are equal, for example if lambda 1 is equal to lambda 2, if both are having the same value, in such cases, so we cannot diagonalize the matrix A. So you have to remember this. So for the matrix to be diagonalized, all the eigenvectors or eigenvalues must be different.